Okay, let's continue. So we know what we want to do, right? We have a formula for predicting yi. Yi is the true value, the true, for example, the true price of a house. Y hat I is our estimate, calculated based on this regression formula. Okay, we want to find a line or a linear equation so that if we plug in a given size, in that example, then we get a predicted price. And we want the difference, the estimation or prediction difference, to be as small as possible. So that means given all the data points from 1 to n, we want to minimize some overall measurements of errors. Here, statisticians, they say that, how about this? Let's minimize the sum of squared errors. Okay, sum of squared errors. So what I want to do is to, okay, sorry, here is the summation. What I want to do is to minimize this thing. So for each error, I square it and then sum them up. So the formula can be just expressed in this way. My true value, my predicted value, and I want to minimize this thing. I want to minimize the squared errors. Okay, the squared errors. There is one thing that we want to say is that when we take the square, obviously we are avoiding the problem that if we just sum up all the errors, then positive terms and negative terms will cancel each other. Then that measurement is not good enough, right? So we can have multiple ways of doing that. We may take the absolute values, we can square it. We have at least these two options. And square is used more often in practice because it helps us to enlarge the big errors we make. Okay, so that's the basic principle behind that. Anyway, so at least you can relate variance and sum of squared errors, right? Because they are all taking square for errors. Okay, so our task is to find beta 0, beta hat 0, and the beta hat 1 so that we can minimize the sum of squared errors. Okay, this is called our least square approximation. We have squared errors and we want to make the squared errors the least. Okay, that's our plan. We want to find such a line by finding beta hat 0 and beta hat 1 so that we can minimize this error measurement. So as an example, when we have 102 as our estimates, we can do the calculation for y hat I all here and get the epsilon I and epsilon I square, blah, 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 blah. If we sum up all of them, that's going to be this number, okay, 16,667. If we choose a different set of estimates, 102.4, you may want to verify that indeed we are getting all these squared errors. Okay, if we sum them up, the sum of squared errors becomes smaller than this. So that means, according to that definition, this particular set of estimates is a better estimate because the sum of squared errors is smaller. Okay, so we want to search among all possible combinations so that we can minimize this sum of squared errors. So what's that? Let me tell you in the next slide. So the least square approximation problem can be solved with a closed form formula in this way. So obviously we don't want you to memorize this formula, or we even don't want you to understand this formula. But what we want is to show you that first, there is a formula, okay? And the second, the formula depends on xi, yi, x bar, and y bar. That's all. That's all. And x bar, y bar are the sample means for xi's and yi's. So that means you can calculate beta hat 1 and the beta hat 0 just from your given sample data. Okay, so I give you 12 numbers. I give you 24 numbers, 12 sizes, 12 prices. You plug in these two formula, you are going to get beta 0 hat and beta 1 hat, and then you are going to minimize the sum of squared errors. That's it. And given that you have formula, obviously you can use software to help you plug in numbers, right? Because all you need to do is to get xi, yi and plug in this formula. So there's no reason for us to do it by ourselves. Software will do that. Software will do that. Okay, so for our house example, if we really plug in the formula here, you may want to verify that our solution is this one. Not too far from 102. It's around 102 and 2.1. Okay, and its sum of squared error is around 13 thousandths. So this is the best we can do for the given 12 sample points. Of course, we will never know the true values of beta 0 and beta 1. Some scholars, they even believe that no such optimal, no such true values exist. However, we still need to do something, right? Because we need to solve practical problems. So according to our sample data, at least the best we can do is to use our least square approximation coefficients to be our estimates. That means we tend to believe that beta 0 is 102.7 and the beta 1 is 2.2. Okay, we tend to believe. And then we will use these two numbers to do our prediction because we now have a formula. So our regression model is to say that y equals 102.7 plus 2.2x. So that means in the future, given a house whose size is x, I'm going to use this formula to calculate y as my prediction. Graphically, we have those 12 points, right? And this is the line that is governed by 102.7 plus 2.2x. Okay, so that means in the future, if I get a house whose size is, for example, 80, then I'm going to predict that its price should be around 280, something like that. So that's the idea. That's the idea. Okay, with this formula, we can actually have one interpretation, is that when the house size, when x increases by 1 unit, in this example 1 meter square, we expect the price to increase by this amount, okay, by 2192. So that means this particular coefficient help us measure how one independent variable affects the dependent variable. Okay, the slope is 2.19, and then the physical meaning is that when the house size increases by 1 meter square, the price is going to increase by around 2000 in expectation. Of course, you will use the formula to make such a claim only if you are considering one house, and if that single house gets larger, what's going to happen? When you compare two different houses, there must be some other attributes that are not the same. Okay, their locations may be different. The age of the houses may be different. So you can claim this 2000 increment for the increase of 1 meter squared only if all other conditions remains the same. Okay, so that's something you need to know when you make this claim. If you are wondering, well, how could that be possible? How could two houses being the same for almost all other attributes? Well, it cannot. So that's why we need some other models to incorporate more variables to be considered later. There is one dangerous thing to do. When we want to do the interpretation, we sometimes want to plug in a number and use that formula to predict its price, right? But we all know that for our given sample data, we have lower bounds and upper bounds for x. It's around 45 to 110. So that means if we want to plug in a number that is outside this range, we can still do that, but we need to be careful because the result can be quite problematic. For example, if we just use this formula, we're going to get a prediction that if a house whose size is nothing, we will still need to pay around 100,000 for that house, which is just impossible, right? So when your x falls outside the range of your given sample data, it's still possible for that prediction to work, but it's also possible that the estimation is just bad. Okay, something to keep in mind. Okay, the best thing of regression is that it can easily be extended to consider more than one independent variable. So, for example, suppose we have the number of bedrooms for each house, okay? Number of bedrooms for each house. Now we have two independent variables, size and the number of bedrooms. We want to use both of them to predict price. So we first, again, form our belief. We believe that these variables have a linear relationship with our variable y. Okay, y is the house price. We believe that house size and the number of bedrooms affect yi in a linear way. Okay, and once we believe that, we can plug in these numbers into another formula. Okay, if you go back to a few slides ago, you see a formula for beta hat 0 and beta hat 1, right? Here you have multiple beta hat. You have beta hat 2. In the future, you probably have a lot of independent variables. So you may have beta hat 3, beta hat 4, blah, 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 whatever. And that formula also needs to be expanded. But given that we will just plug in numbers, there is no reason, there is no need to write down that formula for you to see. Okay? So just know that there is a formula. There is a closed form formula for you to plug in numbers. That's good enough. Software will plug in numbers for us. Okay, so we can do our estimation and calculate the optimal beta hat 0, beta hat 1, and beta hat 2 as these three numbers, 82, 2.8, and negative 15. Okay, so we get our regression model. If this is really the fact, then what does that mean? When the house size increases by 1 meter square, we expect the price to increase by around 2,800. You can see that this number becomes larger than that in the previous example. Previously, it's just around 2.2, but now it becomes 2.8. That difference is possible because now we have another variable that does not exist in the previous model. Okay, and so what's the impact of the number of bedrooms? The formula tells us that if we have one additional bedrooms, then we're going to have the house value decrease by around 16 or 15,000. Okay, that means if you have more bedrooms, the price will decrease. Well, this can be weird, right? Because ideally or intuitively, if a house has more bedrooms, then typically that's a better house, or the house becomes larger, right? So we shouldn't see the price decrease when the number of bedrooms becomes larger. But of course, if you think about the idea of the regression models, then you know why. This number is saying that if all other independent variables remain the same, then when x2 increase by 1, what's going to happen to your house price? So that means your house size is the same, and then you add bedrooms into that house, okay? Then obviously there's no reason that it's always a plus, right? So it's possible that that increment can actually hurt your house price. And moreover, if we think about the value of a house, actually the number of bedrooms is not so practical, it's not so important. What's more important may be size, year, location, and so on and so on. Some people prefer a lot of bedrooms, probably because they have children. Some people prefer fewer bedrooms but a larger living room, for example. So it's really not a very good idea to use one single formula to know the impact of the number of bedrooms on price. So that's why we can get some numbers that is really weird. Okay? So there are a few things to do. First, once we get a model, we need to interpret the result and determine whether the result is meaningful for our application. In our application here, the number of bedrooms may not be a good indicator of house price, may not be a good indicator. Of course, from applications to application, if we zoom into a small region, if we are only talking about one kind of houses whose property is special for one specific way, then probably the number of bedrooms can be very influential. Okay, but at least we know in our example, according to our sample data, x2 does not have a reasonable way to impact y linearly. Okay, this model may be problematic. So we now need some more tools. We already have one tool, that is the least square approximation. Software can help us to plug in numbers and get these coefficients. That's good. But we need to do some more. We need to justify the overall quality of a given regression model. Okay? Now we have at least two models, two equations, one with x2, the other one does not. We need to know which one is better. So that means we need to compare multiple regression models. And finally, we want to test the significance of regression coefficients. We want to know whether this and that are really some reasonable estimate of our population parameter, or whether this variable really affects our dependent variable. So there are a few things to do. We call it a model validation. That's the topic for the next video. Thank you.